Okay, welcome back again. So we continue working on optimal control theory. Now let me write the present value Hamiltonian and the first order conditions again. So the present value Hamiltonian is defined in this way: your objective function ut xt t e to the minus rho t plus your constraints n pit fi ut xt. Okay, so the first order necessary conditions are: first we have the derivative of the Hamiltonian with respect to the control variables, satisfying that. Okay, ukt equals 0 and ukt greater than or equal to 0. Then we have the constraints themselves. So for xit dot, this must be equal to ut xt and t. This is for all I. This is for all k. Then you have the costate equation, basically pit dot equals minus derivative of the Hamiltonian with respect to xit. Again, this is true for all I. And finally, you have the transversality condition. Limit t goes to positive infinity, pit xit equals 0. Once again, this is for all I. This is the costate equation, and this is the transversality condition. Okay. Now the second order conditions are very simple. Let me use this space. Second order sufficient conditions, or second order sufficiency conditions. First, we require F0 is concave. Okay. Then we require Fi's are concave. This must be true for all I. Then we also have, of course, PIT non-negative, all IT. All right. Then the optimal path that satisfies the first order conditions imply the maximum. Okay. Well, if you have additionally, if F0 is strictly concave, okay, then the optimal path is unique. Okay, so that's an additional constraint. So if you want a unique path, we want the reward function F0, or generally it's a utility function, to be strictly concave, and then the constraint functions, the laws of motion, to be concave, and then these remaining non-negative, so this PIT is remaining non-negative. Then if there is a path satisfying 1, 2, 3, and 4, then that path will give us the solution. Okay? And when I say a path, of course, what I mean is ukt for each k and t, xit for each I and t, and pit for each I and t. So I want to solve for these things. And from these, I only know xi0, right? Initial values are known. Then the optimality constraints are found. Then I try to construct a dynamic path, which is supposedly optimal under these constraints. Okay. Now, I will also show you, so this was the present value Hamiltonian, okay? This was the present value Hamiltonian, right? Because I discounted it. Now I can write the current value Hamiltonian. Okay? The current value Hamiltonian obviously will have only the reward function here. Okay, no discounting. And then we use Q to denote current value shadow prices. Okay, and in general, we have this relationship times e to the rho t will be current value Hamiltonian, right? And p it times e to the rho t will be qit. Okay, so this is current value Hamiltonian, and this is for all I current value shadow price. Okay, now first of the conditions can be written in terms of H and Q. Okay, so we have once again we have with respect to control variables, I have this. Okay. Then I have the constraints. They are the same. Right? Constraints are the same. Then the transversality condition will look like this. Limit t going to positive infinity, right? I have, so what is PIT equal to? PIT is equal to QIT e to the minus rho t, right? So I have QIT e to the minus rho t times XIT equals 0. All right? And then finally, I have the co-state equation. Now, co-state equation becomes what? Now, PIT dot becomes what? How do you write that? So it is the product rule, right? So QIT dot times e to the minus rho t plus minus rho e to the minus rho t times QIT, right? So if you write this, QIT dot e to the minus rho t plus minus rho e to the minus rho t QIT. Now this will be the derivative of the present value Hamiltonian with respect to XIT. Okay? Now this could be written as, if you look at it carefully, this times e to the minus rho t, right? Okay, let me. So this is your fourth equation. So this will be e to the minus rho t. Oh, of course, sorry. There's minus here. I'm sorry. There's minus here. Right? So if you cancel out minus rho teams, so if you cancel out these terms, what's it you're gonna find it? Well, you find QIT dot minus rho QIT equals minus the derivative of the current value Hamiltonian with respect to XIT. Okay. So as you see, they are the same thing, right? As long as you have these equations, these definitions, they lead to the same set of conditions. Okay, of course, the interpretation is different, right? I mean, when I talk about current value shadow price, I looked at the shadow price of this resource at that particular T, not today, right? Because if I want to discount that value to present value terms, I want to multiply it with e to the minus rho t. Okay, that's the main difference. Then of course I change that, and of course I replace this with, so since this is the product, right? So H is equal to H tilde times e to the minus rho t. So that's that. Sorry, that's not correct, obviously. Okay, that's it. So now, if you do not have any questions, I will move forward with examples. But if you have questions, I can answer them. We can discuss. If I was unclear, I can re-explain. So at first glance, this looks a bit complicated, but if you think about it, it is not. If you sit down with your pen and paper and write down these things, we are just trying to find an optimal path that will respect certain constraints, and those constraints force me to use my resource efficiently for my benefit. That's the same thing with the static optimization idea. But since now we have dynamics, I have to adjust the values I attach to these resources in time, so that we have the cost-state equation. Okay, the cost-state equation allows me to make this adjustment optimal.
So which one we use? Present value Hamiltonian or current value?
Whichever you prefer. I usually prefer working with current value Hamiltonian because it is easier to write. I don't really deal with the discounting terms, right? It's easier, but sometimes we're gonna, for instance, we will have a bequest problem. So we will have an agent, in one of the examples, we will have an agent. That agent will accumulate wealth throughout her life. At the end of her life, she will give some bequest to her kid. In that problem, there is an end value, right? There's an end date where she dies. At that date, we're gonna look at the present value of the bequest. Okay, present value of the wealth, so that we're gonna equate the present value of wealth to the marginal utility of the bequest, for instance. Then we're gonna find how much bequest she's leaving to her kid. So you can use whichever you want. It doesn't really matter, especially in the infinite horizon problems. Okay. If you have no more questions, let me give you a couple of examples and let you see how do we solve it. Okay. So let me just return to the typical problem of optimal growth. So there's utility, there's discounting, rho is positive. we are choosing consumption. Then this is subject to a non-negativity constraint, a capital accumulation equation where F is a production function. Now let me also add this dilution because of population growth, okay? Now suppose that in this economy there's population growth, so the workforce also grows, okay? So if you imagine a production function which is, for instance, Cobb-Douglas, okay, then total output divided by workforce could be written in this way, right? Where KT is KT NT, because this is constant transfer scale. So then in your capital accumulation equation, you have what? You have K dot T, right? NT minus N dot T KT divided by NT square, right? So you have K dot T divided by NT minus N times KT, because we define N as the growth rate of workforce, okay? So then you have the investment here, right? So if there's no depreciation, per capita investment is this, right? So this is basically per capita investment. And C is, of course, per capita consumption. Okay? Then we also have K0 greater than 0. Okay, so the current value Hamiltonian would be UCT plus QT FKT minus CT minus NKT, right? Then we have the first of the conditions. So this is again Hamiltonian UCT plus Q FKT minus CT minus NKT, right? So I have U prime CT, U prime CT minus QT less than or equal to 0. CT times U prime CT minus QT equals 0, and CT greater than or equal to 0. Then I have K dot T equals FKT minus CT minus NKT. Then we have Q dot T minus rho QT equals minus the derivative of Hamiltonian with respect to KT. So this is equal to, how do you write it? First I have Q, right? Then I have, so let me do this. Then I have F prime KT minus N, right? Then we have the transversality constraint. So limit t goes to post infinity. We have qt e to the minus rho t times kt equals 0. Okay. Now, the trick here, the trick we're going to use is this. So if the utility function is well behaved, we may imagine that consumption will not be different than, so will be different than 0. Okay, so this will be an interior optimum. Then in this case, we're going to have this result, right? So this does tell me what? If I know something about the marginal utility, if I know marginal utility function, then this must be equal to the current value shadow price of capital stock. You may think about this. You should think about this. Why is that happening? Because if I want to consume more today, right, I obtain some utility, a marginal utility that you see on the left-hand side. Well, on the right-hand side, I have the marginal cost, right? Because that is the cost of violating this constraint, basically. And if I want to consume more today, I'm gonna pay this price. I'm gonna face this marginal cost, because instead of consuming today, I could have saved more for tomorrow, right? So that's the notion. Then if you imagine that this is just a function of consumption, you can actually derive Q dot here, right? Q dot here, then Q dot is also here, and QT is related to the marginal consumption. Then you will have, at the end, either a system of Q dot and K dot, right? Or if you use this, you're going to have a system of C dot and K dot. Okay? Now, to proceed further, let me assume that utility is logarithmic. This is the simplest case you will see. And production function is Cobb-Douglas, okay, where alpha is between 0 and 1. Okay? Now then what's happening? Well, U prime C is equal to 1 over C, right? This is QT. Then Q dot T divided by QT, the growth rate of Q, must be equal to minus the growth rate of consumption, right? Because their multiplication is fixed. If the growth rate is here, let's say minus 2%, okay, then this must be plus 2%, right? So this multiplication remains fixed. Okay, that's the idea. You can of course write this. If you want to see how I did write that, you have this, right? CT, you have QT equals that. Then Q dot is equal to minus C2 to the minus 2 times CT dot, right? Then you have Q dot T minus 1 over CT, C dot T, C. But this itself is Q, right? So you have this. So then, in the production function, I have FKK to the alpha. So F prime K, the marginal productive of capital, is this. Okay. So then what do I have? Look at this equation. I have, let me just erase this for a second. So here I have Q dot. Q dot, actually, if I divide the entire thing by QT, I have this. Q dot T divided by QT minus rho equals minus F prime KT. What is F prime KT? Alpha KT to the alpha minus 1 minus N, right? So what do I know about this? Well, it is again related with C dot T, right? So I have something like this. Minus C dot T CT equals rho plus N minus alpha KT to the alpha minus 1. Or you can actually write this in this form. Let me use this space. CT dot divided by CT equals alpha KT alpha minus 1 minus N plus rho. Okay. So then from the constraint itself, you also have K dot T equals KT to the alpha minus CT minus NKT. As you see, let me rewrite them in a new page. So I have CT dot equals CT times alpha KT alpha minus 1 minus m plus rho. Okay, and I have KT dot equals KT to the alpha minus CT minus n KT. Now this is a system of nonlinear differential equations for CT and KT. Right? Now, what do I know about this system? Oh, by the way, I haven't still checked the transversality constraint. Okay, don't forget that. So this is QT to the minus rho T, KT equals 0. Don't forget that. T goes to post infinity. So what do I have here? I have a nonlinear dynamical system. I want this system to start its evolution from K0, right? So at T0, I have to choose some C0. But then starting in this position, so this is what I choose. Starting at that point, the system should obey these equations. All right? And if at the end I have this condition satisfied, this is a solution. Why? Because U is logarithmic, so it is strictly concave. And F is Cobb-Douglas. So the constraint itself is also a strictly concave function. Okay? So if I find a path, again, that satisfies these equations, and when I choose C0, then this will be the unique optimal path. Okay? Now, one thing we can do at this stage is to draw it. Okay? We can draw it. Now, what do you see here? What about steady states? Let's look at the first equation. The C dot equals 0 locus either feature C equals 0, right? And any K would work, or it would feature alpha KT alpha minus 1 equals m plus rho, right? So then that would imply a particular KT value, and it is actually equal to alpha m plus rho 1 over 1 minus alpha, right? Some KT star. Then given this KT star, any C would be defined on this C dot curve, right? This and any CT. But then we have this equation. So K dot locus, if you think about it, K dot locus is CT equals KT alpha minus NKT, right? K dot equals 0 is satisfied only by this equation. So you have something like this for K dot, right? Because you have this and this, right? This is NKT, this is KT to the alpha. The difference between them would be something like that. Okay? And then I have either, again, C equals 0, okay? Or K is equal to this particular number. Okay, so if this is K dot equals 0, C dot equals 0 is that. And K star here is equal to, again, alpha divided by m plus rho 1 over 1 minus alpha. Okay? So this part is not really a solution, right? So we cannot say it's a steady state. So there is now then a unique steady state. So this one, again, forget about this one because it is not optimal anyhow. So there is this steady state now. Is it unique? Yes, it is unique. There's no other steady state which is positive, which has positive consumption, right? So the idea then is to understand the dynamic behavior here. Why? Because I still want to understand that, right? I still want to understand whether this dynamical system satisfies the transversality constraint. So, again, let's look at it once again. So there is a K dot locus. There is a C dot locus. Okay, so if I write them, C dot T equals CT times alpha KT alpha minus 1 minus M plus rho, and K dot T equals KT to the alpha minus CT minus NKT. All right, and this value is K star, okay, and K star is alpha divided by M plus rho 1 over 1 minus alpha. Okay. So there are 4 points where I should understand the dynamics of the system, right? There are 4 regions basically. So to do that, I do what? First, if I look K dot T, and if I take the derivative with respect to C, it's equal to -1, right? So in this direction, this is the direction that CT increases. It is negative, so it must be positive, 0, and negative, right? So I have positive, 0, and negative. So above the blue line, capital stock is decreasing, sorry. Above the blue line, capital stock should be decreasing, okay? And below the blue line, it should be increasing, okay? Now, if I look at C dot T, I can take the derivative with respect to KT now, right? Now, that derivative is CT times alpha minus 1, KT alpha minus 2, right? Right? So if you realize that this is negative, right? So this derivative is always negative because CT is always positive. Okay, and KT is positive, obviously, right? So in this direction, we have plus and negative, right? So in this direction, I have plus, 0, and negative. So on the left of the C dot curve, consumption should increase, okay? And on the right, it should decrease. So there I understand the global behavior of the system, right? Here I understand the global behavior of the system, and it looks like a saddle path, right? It is it's a saddle path, it's a saddle point equilibrium, this one. So you may imagine if I draw a particular version of it. So this is K dot equals 0, this is C dot equals 0, C, K. You have this dynamic here, this dynamic here, this dynamic here, and this dynamic here. And this is your steady state, and then you imagine there is a path going like this, where it is the only route to the steady state. Okay. Now I will stop here. This is the middle of this analysis, I know, but I have to explain this further. This is highly important. If you have questions and comments, we can log in back again, but I will not give you any new content other than your questions. If you do not have any inputs, I'm going to end the lecture for today. Again, next week, we're going to continue with the same model, exactly where I am, from exactly where I am. And that's it. We have less than a minute, so speak up.
Can we do more?
One more session?
No.
Huh?
Can we do more example next week?
Yeah, of course. We're gonna start from exactly where I am now, and I will show you more examples. We're gonna spend more time on optimal control theory, obviously.
Okay.
All right then. I will see you next week.
Thank you.
Okay, thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.